Welcome to lecture 27 on VC dimension. Today we are going to talk about one of the most useful things in machine learning theory, which is how do we understand the fundamental limitation of a machine learning algorithm from the perspective of the intrinsic model complexity. And we are going to measure this model complexity using the notion called VC dimension. So today we are going to spend two parts on this lecture. The first part we will talk about this concept of dichotomy, something that we introduced in the last lecture. And then we are going to talk about how do we use this dichotomy concept to introduce another concept called shattering. And from shattering, we are going to understand the meaning of VC dimension. And from VC dimension, we can talk about the fundamental limit of a learning algorithm. The second part of this lecture, we will spend time discussing several examples of VC dimension. How do we calculate the VC dimension for rectangular classifiers in a 2D space? And how about the perceptron algorithms? And also there are different cases of the perceptron algorithm that we can analyze. So to start with, let's remind ourselves what do we mean by probably approximately correct. This is a very general framework that we use to describe a machine learning algorithm. And by probably correct, I mean that we're using a probability measure to measure the confidence level where you are measuring against between your in-sample error and also the out-sample error. Here, in-sample error is also called in the training error. The out-sample error is called the testing error. And so if you look at the equation here, inside this bracket, you have an event where the in-sample error compared to the out-sample error is less than epsilon, and epsilon is what we call the accuracy. And so if this is smaller than epsilon, that means the in-sample error is very close to the out-sample error, and you want this probability to be high. And so I set a parameter delta, and delta is usually a very small number. And if you have this equality to hold, then we say that this is a probably correct. The other notion is called approximately correct. What it means is that I'm not only looking at the probability, I'm not only looking at the confidence, I'm also looking into the accuracy inside the probability, which is the events that I'm considering. And so in this event, I'm measuring how close is my E in compared to E out. If this holds, I say that it is approximately correct. So if you can ever find an algorithm A such that for any delta and any epsilon, there exists an N such that whenever it's big enough, and then you can make the inequality to hold, then we say that the target function is PAC learnable. So anything that we're describing in this part of the lecture, we will focus on the PAC learnable framework. And by PAC learnable, we mean that we want to have a correlation between the testing sample and also the training sample. As I have mentioned before, if you do not have this kind of correlation, then learning is not feasible. So in the last lecture, we also discussed there were some issues about this PAC framework, because if you understand the half-thing inequality that's underlying the PAC framework, we're only looking at one particular event. Okay, so we're only looking at one hypothesis that come out of your training. We are not looking at all the possible hypotheses that you have a way to choose from while you're considering the learning procedure. And so the difference is that if you really want to go into the training, then you will have a sequence of different events or a sequence of different hypotheses to choose. And these are denoted by H1, H2, all the way to HM. And now, if you want to compute what is the probability of getting a bad event, and bad event is defined as one of the hypotheses has a training error bigger than the testing error, then you are actually considering a sequence of OR events. And in this case, then you're taking the probability of all these OR, and according to the union bound, then you can bound it using a sequence of summations. Now, the problem of the union bound, as we discussed last time, is that the union bound is only good when the events, they are not overlapping. If the events, they become overlap, then you will run into some problem, because then the union bound becomes an overestimate of the underlying phenomenon. and therefore we want to come up with some metric to mitigate the issue that is happening in this union bar. Can we try to understand the overlapping region so that we can minimize the impact of these overlapping regions to the union bar? So last time we introduced this concept called dichotomy, and dichotomy will help us to understand what is the effective number of the model that can actually tell us how much overlap are there in the as we have discussed in the here how much overlap are there in the B's. Okay, and so let's look at the dichotomy. How do we define this dichotomy? Well, the dichotomy is defined as a measure. Okay, it's a number that is that's taking a set of input data points x1 through xn, and then I call it h. H will be the hypothesis set. I'm applying this hypothesis set onto this data points, and then I'm going to return you another set of results. This set of results, they are defined according to a string or a numbers if you want. In the case of binary classification, these strings will either be -1 or +1. Okay, so let's look at the example below, which is something that we have discussed last time. Suppose you have 3 data points in the 2D plane and they are located in A, B, and C as I'm showing you here. Then, if you try to draw one yellow line, which is the linear classifier, then you will have -1, -1, -1 in the first case, which says that all these 3 blue points, they are below your yellow line, and so they have a number of -1, -1, -1. Now, if you change your yellow line to the second case, then you have +1, -1, -1. Okay? And therefore, all these strings, all these numbers, -1, -1, -1, all these numbers, they represent a dichotomy, or in other words, they represent one case that can be classified according to the yellow classifier that I'm defining. So this concept of dichotomy is very useful. It tells us that suppose you give me the data points, and then you tell me the configuration of all these data points, I'm going to tell you what would be the number of events that you can classify them separately. Okay, so here in this case, if you have 3 data points, there will be altogether 8 number of dichotomies that you can ever construct from these 3 data points. So the dichotomy is a very useful thing. It tells us 2 things. One, it says that you need to first tell me what is the underlying data points, and it has to be x1 through xn, and this is usually a finite set of data points that you are considering. And given this set of data points, now I do not need to worry about what would be the number of hypotheses. Rather, I will just need to worry about the number of dichotomies that can be generated from this training data set. Now, the second thing would be that the dichotomy that returns you is a set. It's not just a number. It's returning a set, and the set contains all the possible cases that can be classified differently using the classifier. A dichotomy, if you try to understand this dichotomy, there are cases where if you put the data points in certain locations, then the dichotomies may not exist. For example, if you look at this case, if I put the 3 circles on the blue on the same line, then if you try to calculate the dichotomy, then there are 2 cases where the dichotomy is not able to exist. For example, at the 2 bottom examples here, one would be this case where you are not able to draw a single straight line and try to classify the 3 dots into 2 halves. Okay. Same for the last example there, where you have 3 dots, which is a +1, -1, and +1. In this case, you are also not able to draw one single line and classify them into 2 halves. And therefore, in this case, the number of dichotomies is just 6, compared to the previous slide where you have 8 dichotomies. So you can see that the number of dichotomies really depends on the configuration of the data points. So what do we do? Well, what we can do now is try to think about how can we link this concept of dichotomy to the problem of the union bound, where we have a big m factor here, which we understand that this m factor can go to infinity, even if you're considering a very simple linear classifier, because m is really the number of hypotheses. And if you're looking at a linear classifier, then indeed you will have infinitely many possible classifiers that can be drawn on the 2D plane. And so what we want to do is to leverage this concept of dichotomy and try to map it to this m and see if we can replace the m using the concept of dichotomy. And so last time we introduced this idea of can we use something to replace the m, and then we introduced the idea of growth function. So let me just try to remind everyone, what do we mean by growth function? The growth function, it is a number. It's no longer just a set, okay? It's a number that calculates on the dichotomy set, okay? So here you have, on the right-hand side of this equation, you have this maximum applied to the sets, and the sets will be the dichotomy. And the absolute value that I have here will be trying to calculate the number of dichotomies inside the set. Now, remember, this dichotomy set is, of course, is a set depending on the specific configuration. If you put the 3 dots in a triangle, then the number of dichotomies can go to 8. But if you put the 3 circles along the same line, then you will only have 6 dichotomies. And therefore, this number depends on the configuration x1 through xn. Now, if I put the maximum operation, that I'm evaluating this number of dichotomies by calculating the maximum configuration. That means I can move around my points and want to find a configuration such that my dichotomy number goes to the maximum number. Then I can define a thing called a growth function. So the growth function is really the maximum number of dichotomies that can be ever constructed using n data points. So if you look at the equation that on the right, on the left, you can see that this definition of the growth function is mh on n. That means it is a number that depends on the hypothesis sets. The hypothesis sets will tell you what is the hypothesis that you can use. For example, a straight line or a quadratic classifier or deep neural network, that will define you the hypothesis set. And then what is the n? N would be the number of dichotomies that you're considering. It would be the number of training data points that you're considering. And so you can configure the number of training data points. You can move these n data points left and right, up and down. You can move in this space. And then you can try to calculate the dichotomies as I'm showing you on the right-hand side. Then you calculate the maximum. That would be the growth function. So in other words, you give me a hypothesis set, and then you tell me there are n training samples, and my job is to do whatever I can by allocating the x1 through xn and tell you what is the number of dichotomies such that that number can be maximized. And the maximum number of dichotomies here is the best I can ever do with the hypothesis sets that you give me, and that will define me the growth function. So mh of n is really a measure of how expressive is your hypothesis set. And so if you have a large mh, then that means you have a more expressive h. That means you have a more complicated hypothesis set. And so mh of n only depends on h and n, and it doesn't really depend on your learning algorithm A, and it doesn't depend on the underlying distribution px, because I'm really calculating the maximum over all the possible samples in your training set. Okay, so now we have what? Well, we have the dichotomy, and then we have the growth function. And so we ask, can we ever replace our m by this small m here? Can we replace the number of overlapping regions by the growth function? Now, this should sound very natural in the sense that originally you start with a hypothesis set. That is an extremely large set of hypotheses. And now you shrink this hypothesis set into something that only depends on the training samples. So if you have a set of training samples, I can define the growth function, and then this growth function will somehow be able to measure how complex your model is. Now, if you do not do this, then you are stuck with the infinitely high dimensional hypothesis set, and you have no way of overcoming it using the union bound. But using the growth function, you're only looking at the finite number of training samples. That seems to be hopeful. Now, how can this growth function be ever used in terms of replacing the m? Then we can think about the assumption that we are making about the p. Here, the p is the distribution linking the testing set and also the training set. Because we are assuming that there is a correlation between the training and also the testing, and therefore, whatever that you are doing with the training should carry some message towards the testing. And therefore, instead of worrying about the infinitely many hypotheses in the hypothesis set, by just looking at the training sets, by looking at the growth function, in principle, I will be able to calculate something that is representative enough for the entire hypothesis set. Okay, so I want to summarize a few examples that we have come across before. How do we calculate the growth function of different scenarios? So suppose you have a hypothesis set being a positive rate. We show that the growth function, that number is n plus 1. If you have a positive interval, then the growth function will have a number of n squared divided by 2 plus n squared divided by 2 plus 1. That is the order of n squared. Now, if it is a convex set, we show that the growth function would be a function of 2 to the power n. That is the largest possible number of dichotomies that you can ever get on a finite set. So now, if we replace the m by the small mh, and if the mh of n is polynomial, then we are in good shape, because then this polynomial growth of the mh will be override by the exponential decay on the halving inequality that we have been discussing. Alright, so now I want to introduce one more concept. It's called the shattering. So the definition of shattering is the following. If a hypothesis set H is able to generate all the 2 to the power n dichotomies, then we say that H can shatter all these data points. Right, so what do I mean? So you can think about the 3 data points in a 2D space as an example. So you have 3 data points, and then you ask, what is the number of dichotomies that you can ever generate? Well, you can generate 6 dichotomies, you can generate 8 dichotomies. We ask, what is the maximum number of dichotomies that you can generate? That will be 8. Okay, so that's an example that we've seen before. Now I can ask, what is all the possible number of dichotomies that you can generate ever possible from a set of 3 data points? And that will be 2 to the power 3. That's also 8. Now, since the number of dichotomies that we are able to generate compared to all the possible numbers that these two are matched, then we can say that our linear classifier in the 2D space will be able to shatter all these 3 data points. So that's the concept of shattering. Shattering will tell you that whether you can ever reach the highest possible number of configurations that you have with the training data points. So the difference between a shattering and also the number of dichotomies is that the number of dichotomies still depends on the configurations. Okay, it still depends on the x1 to xn. The concept of growth function says that I'm going to calculate the maximum. Now the maximum is still not there compared to the number of possible configurations you can ever draw from the n samples, because the possible configurations you can ever draw from any n samples will be 2 to the power n. If you only give me the growth function may or may not hit this number. If it ever hits the number, then we say that the hypothesis set has shattered all these n data points. So the hypothesis is a hyperplane returned by a perceptron algorithm in 2D. This is an example. Okay, so let's think about this example. And then suppose n equals to 3, we ask whether this hyperplane can shatter all these 3 data points. And because can we achieve 8 dichotomies? And we show that yes, it's possible. As long as you allocate all these 3 data points into the triangle, you will be able to generate 8 dichotomies. And that is the maximum number that you can ever get from 3 data points. So what if you have 4 data points? Can a linear classifier shatter? So now you can ask, what is 2 to the power 4? 2 to the power 4 is actually 16. And then we show you that, but if you have 4 data points, if you only have a 2D classifier, the best you can ever do is only 14 dichotomies. The growth number is 14. There are 2 cases where if you put the plus 1 in this way, and then the minus 1 in that way, you put it into a diamond shape, then with only 1 linear classifier, you are not able to classify them. And so with 4 data points, if you allocate the sample into this way, then there are 2 dichotomies that you cannot be able to generate. And therefore, then we ask, what can the linear classifier shatter 4 data points? And the answer is no. Okay, and therefore, what we have shown here is that suppose we have 3 data points in a 2D space. What is the number of data points? What is the can this hyperplane shatter? And the answer is that you can only shatter up to 3. And so that will give you a number. The 3 will give you a number, and that number is what we defined as the VC dimension. So what is the VC dimension? The VC dimension of a hypothesis set H, denoted as D of VC, it is the largest number of n for which H can shatter all the n training data points. So let's take a moment to understand this meaning of VC dimension. So this VC dimension says that you give me n training data points, I am going to look at all the possible configurations, and then I will calculate the growth number. And suppose this growth function can ever reach 2 to the power n, then that will be the VC dimension. So suppose you give me a hypothesis set H, suppose this is a linear model, you tell me that there will be a number of training samples n, and I start with a small n, and then I will be able to shatter for a while, and then I will start to hit a bump. So think about in the linear case, I will start with 2, yes I can shatter, I go to 3, I can also shatter, I go to 4, then I cannot shatter. And therefore, there will be an intrinsic number that governs the model that I have. Because I'm working with a 2-dimensional space and I'm using a linear classifier, the maximum number of data points that I can shatter will be 3. And so this 3 was defining the VC dimension, and that is telling me how expressive is my model. So for example, in 2D, n is 3 is okay, n is 4 is not okay. And so I have found the largest n such that H can shatter n training data points. So in 2D, the VC dimension is 3. Now, if H is more complex, then we should expect to use a larger VC dimension. So think about if you're using a quadratic classifier, then apparently you should be able to use a you should be able to classify a much larger set of data points, and so therefore you can let this VC dimension to grow. Okay, if you have a deep neural network, this VC dimension will go even further. And so this VC dimension is giving us an intrinsic measure of how expressive is your model. If your VC dimension is high, then we should expect that this model is expressive enough, or we can, in other words, we can say that this model is complex enough. So your VC dimension is giving us a way to measure the model complexity. The good thing about VC dimension is that it does not depend on the particular distribution of the training sample X. It does not depend on your learning algorithm A, and it also does not depend on your target function F.